So dear friends, it's a privilege to give this keynote, and let me start by congratulating you at the 15th anniversary of the Global Institute of Sustainability at ASU, a global partner at the frontier of interdisciplinary science for global sustainability, a core partner also of the Potsdam Institute of Climate Impact Research. It's a particular privilege as we enter the super year, or have entered the super year of 2020, when we have so much scientific evidence that this is the year when we decisively need to start bending the global curve of emissions, and a transition also on biosphere stewardship, minimizing biodiversity loss, and starting the journey towards prosperity and equity within planetary boundaries. It's also entering a decisive decade when we know we have our last chance to turn things around and transform ourselves towards a new logic for sustainability in terms of both prosperity and equity. And let me here give you a quick summary both on the scientific diagnostic, proposing a paradigm for the future, and some evidence of our ability to follow exponential roadmaps towards a successful, sustainable future for humanity. There is reason for deep concern. As we know, the Australian devastating fires, the worst ever observed on the continent, having, as you may have followed in media, a potential impact up to 5% of Australian GDP just because of the massive human losses and the insurance claims that are arising from this disaster, potentially even pushing the whole Australian economy into recession. We have today ample scientific evidence of attributions showing that we've passed the point when we can, in the past, often not make links between extreme events such as droughts and floods and storms and different types of heat waves hitting health and economies and anthropogenic global warming. We're past that point. Today we have evidence that humans amplify these extreme events. Now this is occurring already at 1.1 degrees Celsius warming. We have the evidence now that the last 5 years are the warmest years on record, and it's quite important to recognize that already at 1.1 degrees Celsius warming, we start seeing major invoices being sent back from the Earth system into the economy. Now, I think it's always important to remind that this curve is not only a curve of extraordinary warming in terms of the pace and the amplitude, but it's also the warmest temperature, as far as we know today, on Earth since the last ice age. So we are bumping at the ceiling of the hardwired boundary conditions for the maximum variability we've seen on Earth since the last ice age. We focus on the atmosphere. This is a paper that came out just a few weeks ago showing that we've underestimated even the heat uptake in the oceans. The planet is in fact not only an interconnected, self-regulating biogeochemical system, it's a system which functions as a thermostat, with the oceans picking up, shown in the graph to the furthest right here, 95% of the heat caused by our fossil fuel burning and land use change. This is what explains the amplification of major extreme events and regional, changes in weather patterns across the world. In a report that we summarized for the United Nations Head of States Summit in September, the Antonio Guterres, Secretary General of the United Nations Climate Summit, together with the World Meteorological Organization, the IPCC, the Earth League, that I have the privilege of co-chairing together with Peter Schlosser, and Future Earth, we did a super summary of the scientific summaries called The United in Science. I would argue that the most important message from science there is actually the summary of the advancements in research over the past 20 years. And it's summarized in this red embers graph here. The red embers graph is a scientific assessment of communicating risk. The darker the red, the higher the risk for climate-induced changes. On the y-axis here, you see the deviation from the average temperature on Earth before the Industrial Revolution. So that's the 0 point, and you see up to 6 degrees Celsius warming on the y-axis. And you see three clusters of risk here. Furthest to the left are the clusters related to changes in big ecosystems, like changes in rainforests. In the middle cluster, you see the risk, according to the scientific assessment, of inducing extreme events, such as droughts and floods. And furthest to the right, you have what preoccupies and worries us most, namely the risk of us inducing so-called large-scale discontinuities, or to put it simple, catastrophic tipping points. And you can see just the pattern over the last 20 years represented by each of the IPCC, the United Nations Intergovernmental Panel on Climate Change, assessments. So furthest to the left in each cluster, you have the state of science in the third assessment in 2001. Then you have the fourth assessment in 2009, the fifth assessment in 2014, and the 1.5 degrees Celsius report in 2018. So the four columns is a trajectory of 19 years of scientific advancement. And you see the more we learn, the more science we have, the more data we have, the lower is the temperature that can induce unacceptable potential catastrophic risk. The drama is that 19 years ago we assessed that the risk of large-scale discontinuities and major impacts would not occur until we reach 5-6 degrees Celsius warming. That's essentially a zero risk because that's a point that we did not have to be too concerned about, and it's a place we haven't been in for the past 10 million years. Today the risk is down to between 2 and 3 degrees Celsius. That is the new risk landscape. We know with not unequivocal yet, but with rising scientific evidence that 2 degrees Celsius warming is a point beyond which we risk inducing irreversible changes. Now, we have tried to translate this risk landscape into understanding what are the components in the Earth system that can trigger these changes. This is a paper that we presented in Nature in November 2019, for the first time making the 10-year summary of what do we know about tipping points in the Earth system. What you see here on this map are the 9 systems, shown here in black, that have scientific published observations that they are on the move. That systems that we know have evidence of being able or at risk of flipping over, for example, from a rainforest to a savanna, or irreversibly committing the Greenland ice sheet to melting, and that we start seeing signs of rising variability and therefore risk of approaching irreversible points of no return. That is one key message, that 9 of the known 15 systems that contribute to regulate the stability of the whole planet are on the move, already at 1.1 degrees Celsius warming. But the second message here is that we see more and more published research showing that they are interconnected with each other, represented here by the arrows. And it's quite interesting that it seems like the ground zero of much of these changes start in the Arctic. That the Arctic and Greenland are at a point of amplified warming, twice as fast as the planet on average, and that the accelerated warming is triggering changes in ocean circulation, which leads to a slowdown in the whole AMOC, the Atlantic Meridional Overturning Circulation, slowing down the Gulf Stream, which in turn holds more warm surface water in Antarctica, accelerating the melting of the West Antarctic ice shelf. We also have increasing evidence that the changes in the Atlantic overturning is affecting rainfall patterns and the dynamics over the Amazon rainforest that can trigger more droughts and thereby accelerate forest fires and in turn lead to amplified pulses of carbon dioxide when forest dies. These kind of domino effects of intimate cascades between tipping elements is at the scientific frontier. There is a lot of uncertainty, but we're starting to see more and more scientific evidence which lends even more support for 2 degrees Celsius being a point beyond which we may push ourselves into a trajectory that we've called the hothouse Earth pathway, which means that the Earth goes from being our best friend, dampening and reducing warming and stress, which is the state that she has been in and continues to be today actually. 50% of our emission of greenhouse gases are still taken up by land and oceans. But beyond 2 degrees Celsius warming, we cannot exclude that she then shifts logic into a biogeophysical dynamics that could start self-reinforcing warming, meaning that the planet goes to being a foe and becoming a self-emitter of climate forcing. Now, so that is where we are. This is starting to be increasingly understood, as we know. This is the global risk landscape from the risk report of the World Economic Forum in 2020, just a few weeks back. You've probably seen it, the likelihood of impacts on the economy on the x-axis and the impacts on the economy on the y-axis. 2,000 plus business leaders in the world assessing their best assessment of risk for their businesses and economies. And what you find is that in the upper right-hand corner, that climate action failure, extreme weather events, loss of biodiversity, freshwater crisis, the top 5 global risks for the economy are assessed to be today related to planetary boundaries. We also see how democratically elected constituencies at the lower level below nations, like cities and counties, have across the world taken voted decisions to declare states of climate emergency. Over 1,000 have done so. 11,000 scientists recently signed the Science for Future Declaration, providing support to the Fridays for Future youth movement. So we started to see a dynamics of being increasingly concerned over the risks we're seeing. In fact, this has led us to invite heads of state into a dialogue for the first time to explore whether we scientifically have a justification for declaring a state of planetary emergency. That is very serious. It's never been done before, and it would be a reflection not only that we are facing catastrophic risks, but also that the time window is becoming a concern for us, that we now need to transition so fast in order to avoid taking risks that we are at risk of not being able to handle. That is why the Planetary Boundary Framework that we introduced in 2009, updated in 2015, has more relevance than ever as a scientific framework to guide the transformation towards a sustainable, prosperous and equitable future. The 9 systems identified in 2009 have been verified time and time again, and that we can today quantify scientific targets, the boundaries that gives us a safe operating space here in green for climate, for chemicals, for air pollution, for water, nitrogen, phosphorus, biodiversity and land, and of course the climate system, and that these are all intimately linked and regulate the final state for the planet and therefore for people. And as you see here, unfortunately, in the latest assessment, we are transgressing the boundaries on biodiversity, on land, and on nitrogen and phosphorus, and are in a danger zone on climate. So we rapidly need to transition if we want to have a good chance of maintaining our planet in a state that can support humanity. We have, since this publication, a lot of evidence in support of this analysis. This is a geological assessment of temperatures on Earth over the last 60 million years, showing in yellow the Holocene period of 12,000 years, the period of grace where we've developed modern societies. But if we follow the pathway in furthest right, which are the IPCC trajectories, we are at risk of reaching 4 degrees Celsius warming, as you see from the black line here. And if you look carefully what that would correspond to, it would actually mean winding back the climate clock not 1 or 2 million years, but would then be taking ourselves back to a point we haven't seen for the past 5 to 10 million years. That is the drama in the pace of change we're seeing. In fact, in our latest climate modeling here at the Potsdam Institute, we give even more support to a planetary boundary approach to our future by doing for the first time a reconstruction of interglacial glacial cycles over the past 3 million years. You see the graph here, deviation from pre-industrial temperature on Earth on the y-axis. The 0 line is the 14.5 degrees Celsius temperature pre-industrial average. And what you see here in green is the variations back and up and down between glacial and interglacial over the past 3 million years. And the key message is, as far as we can see from this climate modeling, the latest one validated against all the proxy data and ice core data we have, that average temperature on Earth has never exceeded 2 degrees Celsius warming over the past 3 million years. That gives us quite some confidence that staying below 2 has quite an important logic for our future. And this is what it looks like today. The last 2,000 years, a large variability, but look at the hockey stick pattern today with the absolute latest data of 2019. So we are in a blink of time, blink of geological time, really pushing ourselves outside of the range of normality. The transformation must be following what we call the carbon law, cutting emissions by half every decade, follows the scientific pathway towards a zero carbon world economy by 2050. We have now entered the decisive decade, the first halving, which is the toughest one, but which can get the ball rolling towards making the positive transition irreversible in the future. It requires halving emissions every decade, shown in gray here, until 2050, but it also requires a transition in the world food system from being the single largest emitter in dark brown to becoming a net sink in orange, an agricultural revolution. We also, whether we like it or not, need in yellow to invest in large-scale carbon capture and storage scaling to be able to keep climate forcing well below the 2 degrees Celsius warming. And in green and blue, you see the nature-based solutions required to keep carbon sinks intact in natural ecosystems. So we're truly talking about something which is at the heart of the Global Institute of Sustainability, namely an integrated transformation to global sustainability to be able to deliver also on the Paris Agreement. It won't be enough to also decarbonize the energy system. So we have in the Sustainable Development Solutions Network that GEOS is a partner of, identified the 6 transformations that can take us successfully toward the Sustainable Development Goals. These are the transformations that are so well known to us, but it's quite interesting that if we are able to invest in the digital revolution in support of sustainability, not as a self-amplifier of more unsustainable businesses and behavior, smart cities, sustainable transition in the food system, the whole decarbonization of the energy system, of course, circular consumption and production systems in the economy, and finally, building human capacity for equity and understanding the future of health and democracy, we're able to find kind of transition pathways that can deliver towards a more, let's say, equitable framework for humanity within a safe operating space. Now, we have tried to concretize these big transformations into the exponential roadmap. The exponential roadmap is an attempt of answering the question, can we really cut the emissions by half over the next decade in sector by sector? This is the latest analysis presented at the recent World Economic Forum in Davos in 2020, showing that sector by sector with known technologies show that we can, at least with the knowledge we have, deliver a cutting of emissions by half over the coming decade. In industry, in buildings, in transport, in agriculture and food consumption, we have the solutions. The challenge is to get the governance and the policy measures to unleash the innovation pathways at scale. And this is the big challenge. We have the evidence, this is the empirical evidence on solar voltaics and wind power, which over the last 15 years has followed an exponential pathway, starting though at very low levels, but still doubling every 5.5 years. In 2015, it's still only a few percent of the global energy mix, but if we follow that continued doubling pace, it would take us to roughly 50% of world electricity originating from solar and wind by 2030. So it's not if it's complete utopia to really succeed in this transformation, though the pace is very fast and has to be scaled across geographies. The Sustainable Development Goals framework, therefore, can be an important guide to really support this transition. We don't see much traction here yet, though, and it's a concern to me that this is used as a kind of a favorite smorgasbord where you pick your favorite goals and you focus on them, when the science shows that we have to keep them together as what I call a wedding cake, that there are 4 goals that are non-negotiable. Goal 6 on water, 13, 14, 15 on biodiversity, oceans and climate, that they form and provide the planetary boundaries of a safe operating space. And inside those, we can have aspirational social goals, successful innovations in technology and economy embedded within a proper governance structure. That, in my mind, should be the guiding principle for the transformation towards a prosperous, sustainable future. So I'd leave you with this in your anniversary deliberations, a kind of a framing that can potentially inspire some of the research into the future, namely putting the Sustainable Development Goals framework inside the safe operating space of a stable and resilient planet. I think that's the new point we are at in the Anthropocene, and I look forward to collaborating over the next successful decades for the Global Institute of Sustainability. Thank you for your patience.